second day of microcontroller programming workshop. So this is a small recap for yesterday as we learned microcontroller and its peripherals and we knew about GPIO, timer and UART interfaces. So for today, we are going to learn about ADC and pulse width module using timer and how to calculate the duty cycle. Also, we will solve the task and finalize the project. So meanwhile, I would like to thank you everyone for joining and participating in our day 2. And I would like to welcome our speaker, Engineer Anas Ismail, to present.
Hello, thanks. Let me just share my screen.
Yeah, sure.
So this is the second day of the microcontroller programming workshop. So I'd like to start by doing the example for the task I gave yesterday, just to make sure that everyone is on the same page. The task involved calculating the speed of a runner that is passing by sensors. So let's start by heading to Proteus and let's create a new project. So just go to File and then New Project. Then we'll select the name and the path for our project. Let's call this example task. Mind, let's just create a new file. Then you just have to click next. For creating a schematic, we'll just use the default template. So you won't change anything for this screen. We'll just press next. We will not create a PCB layout. So just leave it as it is and then just press next. We are gonna use a firmware project. We're gonna choose the family for our microcontroller, which was Cortex M3. And we're gonna choose our microcontroller, which is STM32 F103C6. Then we'll just press next and then finish. So we have our task project created. We won't need the source code, so we'll just close this. And then let's add our sensors and our virtual terminal. So we need 2 sensors in order to detect when the runner enters the area and then leaves the area. So we're gonna click B on the keyboard. We'll just hover over here and click this B. This will present the screen to pick devices. We're just gonna search for a digital logic. This one, and then press OK. We'll add the digital logic pin. Let's, for example, connect to A8. I think there's another digital one that has animations, which might be easier to follow. We find it. On this one. Search for it. I'm gonna use this one. Let me double check. So we're going to use something to relay either 1 or 0 to the microcontroller. That way we can simulate the switch or the sensor when the runner passes. So you can select the logic toggle. This one. Same, but just has some animations to help us visualize. We'll attach two, let's say A7 and A9. And then we need to add the virtual terminal. We'll go to this one, which is the Instruments tab, and then we'll select the virtual terminal, which is this one. We can mirror it by right-clicking and then pressing on the X mirror. And then, as we've discussed yesterday, inside the datasheet, you can scroll down to the pinout and then see the pins for UART, the UART interface. So if you're using the UART 2 interface, we have the TX and RX as pin A2 and A3. So we're going to connect the RX to A2 and TX to A3. Since A2 is the TX, so we'll connect the TX to the other device's RX. So we'll just connect this one and this one. This is all you need to do for the task, for the schematic part. You can replace this with a push button or whatever you would like to replace with, as long as you simulate the sensor. So let's hop into STM32 Cube IDE and create a new project for the task. So just go to File, New, and then STM32 project. We'll wait for the target selector to pop up. And then we'll choose our microcontroller. We'll choose STM32F1. Then we can expand this one so that we can see better. Scroll down to 103C6. And then press on Next. Let's name this also example task. And we'll click Finish. This is the same as we did yesterday. We'll use the same peripherals also. We're going to use the GPIO for the sensor input. We'll use the timer and the interrupt for counting the seconds between the two sensors. And then we'll use the UART to print the speed. So once the IOC files loads up, we're going to select the pins that we connected to, which was 7 and 9, the A7 and A9, and set them as inputs. So this is a GPIO input. And then also A9 is a GPIO input. Then we'll select the timer. Let's say timer 2. Select the clock source, just as we did yesterday, internal clock. And then we need to configure this to have a 1 millisecond interrupt to get the most accurate speed. Let's make sure the clock configuration is okay. We need to select the PLL clock and then choose 16. This might give an error for the APP1 preferred clock, as the maximum is 36. So we'll just choose divide by 2. Again, this is the same setup that we used yesterday. If you go back, we'll put the prescaler, for example, as 64 or 640. Then we'll calculate the period so that we get a 1 millisecond interrupt. So if we calculate using the equation for the time we showed yesterday, the value will be 100. So this is 100. Instead, we can also use 64 and 1000. Both should be okay. Then don't forget to enable the auto reload preload. The same setup as yesterday, we just changed the period and the prescaler. We need to also enable the interrupt, the global interrupt for timer 2. And that's the interrupt and its timer. Finally, we need to enable the UART2. We will choose asynchronous mode. Let's set it to 9600. Then leave the rest of the settings as is. Once all of this is done, we're ready to generate the code. We'll press Ctrl and S to generate the code. Once the code is generated, we can start writing our main logic inside this while loop. So what we need to do is to detect when the first sensor is pressed or is sensing, start the timer, and then when the second sensor is pressed, we not stop the timer, just stop the counting, and then display the speed. So let's first start the timer interrupt. So we'll use halt time for phase start, then IT for the interrupt. We'll use timer 2. This makes sure that the timer has started. Then let's add some variables. Let's add a variable to determine whether the timer should count or no. So let's say counting, then equals 0. Just let's make it counting. Then this also needs to be accessed inside the interrupt. So let's remove it from main and put it outside in counting. Also add the time itself, but let's make it a float. So float time between the two sensors. And then let's start by detecting the bottom presses or the sensors. We'll do the same if and then all underscore GPIO. Then we'll press on Control and space to see the recommendations. We want to read the pen, and we'll be reading A7. So if A7 is read, then we start the counting. Counting. 1. Also initialize the counting. 0 at the beginning, to avoid any errors. Then do the same for the other sensor, but then we can count, or we can sense when we should count. So let's see inside the timer itself. So if you go to the example task and then go inside our IT file, which is the interrupt file, scroll down, you should see our timer 2 IRQ handler. One thing you can do, instead of including your definition here, is just copy this or cut this and put it inside main. If you go inside main, let's put it directly under the main function. It should still recognize this function as the interrupt function. So here, let's add something. Let's say if counting, or if it's equal to 1, we'll go inside this if condition, and then let's increase the time. The time it's equal, and then 1 millisecond. Since this interrupt occurs every 1 millisecond, so it'll increase 1 millisecond. Okay. If it's counting, then we'll just keep on increasing the time. We need to also add the distance between both sensors. Let's define the distance. The distance, and And let's divide it as 2, for example, 2 meters between the sensors. Then we can start. For this one, let's make sure the time is equal to 0 at the beginning. It starts counting. Put 0, and then you start counting. And then here we'll print the UART speed. So counting is equal to 0. We stop the counting. And then we need something to hold our data. So let's create the data character data. Give it a size of 100. It's an array. And then let's use its printf. Let's include first stdio.h. This includes the sprintf function, so we need to include it. The sprintf function basically loads in, just like the printf, but instead of printing on the console, it prints inside the other variable. So we'll use sprintf data. And then let's say speed equals %f, which is a float, meter per second. Then this is going to be distance divided by the time that we have. You may notice an error. The floating format is not enabled. You can go to Project and then Properties. Once the Properties tab is open, you can go inside the C/C++ build to Settings. And inside MCU settings, you can enable using float inside printf and scanf. While we're here, let's also enable the hex file generation and then apply and close. So now there is no error. Once we have the speed loaded inside, let's make sure it's float. Then let's print it using UART. So how UART transmit this one, we choose UART2. The data is data, and then the size, we're going to use the function called size of data. It automatically calculates the size for data. The timeout, let's set it to 50, for example, and that's it. So now we have 2 sensors. When the first one is pressed, counting is set to 1. When counting is set to 1 inside the interrupt, the timer keeps on increasing. And then when the second sensor is sensed, we stop the counting and then calculate the speed based on the distance between the 2 sensors that we already know and the time that we just calculated. Then we print it using UART. This is just one way of doing the task. Might be the easiest way, but you can do whatever you want to complete the task. So let's build this, see if there's any errors. There are no errors, just one warning for data. And remove the warning by casting it into an unsigned int. And this is an array, so we need to add the pointer symbol. Rebuild again, it should be removed. Nice. So let's go load the hex file inside our microcontroller and then try out our task. We'll go to Cube IDE, your workspace, and then go to the example task, debug, and then the hex file. Let's run this. You can see the virtual terminal is currently empty. And then when we press the first one, it should begin counting. And then when we press the second one, it should display the speed. So for the speed that we pressed just now, the runner was 9.09 meters per second. You can also add the while loop at the end to avoid multiple clicks. Just while the same. Then here the same also. Let's change this to 7. So this is basically the easiest way to do the task, yesterday's task. You still can do the task using this method or any other method. The deadline is today's midnight. So if you still haven't done the task, you can still do the task. So that's it for the task. Let's go back to day 2 and discuss ADC. How is it possible to get the time? The time is incremented inside the interrupt. So if it's counting, the time is incremented by 1 millisecond every time the timer interrupts. We've set the timer already to interrupt every 1 millisecond. So what is the syntax? What is the syntax is the same to miles in Arduino, millis in Arduino, that for use catch input mode in trimmer. I'm not sure what you mean, but this is the easiest way, I think, for doing the task using all the preferreds that we learned yesterday. You just increment inside the interrupt. Let's go back to day 2. So the ADC interface is an analog to digital converter. It's a system that converts an analog signal, such as the sound bit, or for example, the data from an analog sensor, into a digital signal. One common way of using sensors with the ADC is using a voltage divider. So the voltage divider basically prevents the current from overloading the sensor we're using. So we'll put another resistor here. And then the Vout depends on the resistance for the second resistor. If the second resistor's resistance is very high compared to R1, then we'll get most of Vn at Vout, and so on. So we'll use this with an LDR. An LDR is just a sensor for detecting the light intensity. Let's close this project and create a new project for day 2. And I'll show you exactly how we can wire the LDR sensor. We'll just continue using yesterday's workshop. So this is the workshop file for yesterday. And we're going to add the LDR sensor. So if we just search for LDR inside our menu, which we opened by pressing P, this is the first one. Just press OK, and we can place our LDR. We just need one more resistor. We'll add one more resistor. And then we can connect the ground and the 5 volt. We'll go to terminals and then power to add the 5 volt. Also inside terminals, we can add the ground. Then we'll just connect all of them. And we'll take the output from this point. You can directly connect it, but I prefer to use an output label. Output is also inside the terminals menu. Just connect, and then let's call this LDR, for example. Double click and then write LDR or whatever name you would like to call it. Let's then connect an input. somewhere. So we need to know the ADC pins. So let's go back to the datasheet and see which pins can be used for ADC. There are some C pins, but we don't have any C pins for our model. So we'll just have A or B. So you can see if A0 can be used, A1, A2, and so on. We're already using A2 and A3 for the UART, so we'll not use those. So maybe we'll use A1. As you can see, ADC 1, 2, and 1. So let's go back and connect this to A1. And add one input here, and we'll connect it to LDR. We can also double click on this LDR or right click and then edit properties and increase the intensity step. Let's say 100. The max is 1000, so it should be faster to get to 1000 with 100 increments. So what we can do with this setup is once we press the button, we print out the ADC value for this LDR. So let's go back to STM32 Cube IDE, close this project, right click, and then close project. And then let's open the Workshop Day 1 project. So far, is everyone able to follow? Do you have any question?
Any question, guys? I think no question, so you can proceed.
Okay. So this is what we did yesterday. This is the file for yesterday's workshop, but we don't need all of these now. So we'll just comment this and comment this one. Don't need this entire button for now, push button. So we'll just comment it. You can comment by pressing Control and then the / on your keyboard to comment multiple objects. We'll just select and then Control and the /. Anyway, let's say if we read this one, we need to read the ADC value. Let's go first to our IOC file and enable the ADC. So if it does something like this, you can just double click on the IOC file tab, and this will expand it. Then let's go to analog and then choose ADC. We'll be using ADC1 since it has N1 that we need, which is A1, this one, ADC1, N1. Everything, this is the mode for the ADC. You have only independent mode for this controller, microcontroller. The data alignment is whether it's right aligned or left aligned, means that inside the register, the data or the bits will either be aligned to the right, which is the default, or aligned to the left, meaning that the value will change since it's a binary number. These are other modes for the scan conversion mode. It scans first and then converts if it finds something in the ADC, but we don't need this now. The continuous conversion mode immediately starts another conversion once the conversion that started finishes. And discontinuous is the opposite, but we don't need any of these for now. All of these are standard settings, so there's no point in changing them. So we'll just keep them as they are for now. So with this enabled for the ADC, let's press Control and S to generate the code. Yes. You can see once we've enabled the ADC, the clock has changed since now we're using ADC1. So no, we don't want to generate yet. Let's go see what was the problem for the clock. There is an automatic clock solver, but I don't recommend using it. You can just press no. And then this is the problem. The max is 32, but we're now feeding 64. It was not showing an error before because ADC was not enabled. But now that is enabled, we need to select the ADC prescaler. So let's select divide by 2 or divide by 4. Still not enough, then divide by 8. So this is 8, and it has removed the error. Now we can press on Control S to generate the code. The code seems to have finished, so let's go back to the code. You can see that this is the ADC1 initialize that was added. If we press F3 to go to the function, you can see the instance is ADC1 since we're using ADC1. The scan is disabled, continuous conversion is disabled, and so on. These are the same configuration that we just now select. So let's go back to our main and let's start using the ADC. So if one is pressed, this push button is pressed, we first need to start the ADC. So hall underscore ADC, then control space, U. Let's find start. This one, hall ADC start. There's also DMA and IT as the rest of the peripherals have. But for now, let's just choose the normal start. We'll select the ADC one that we have. And that's it. What we can do now is wait for the conversion to end. This starts the ADC and also starts the conversion, as you can see. So we need to wait for the conversion to end. We can wait using this function, hall ADC also. Then there's a function called poll for conversion. It just delays until the conversion is done. So we'll pass the same struct, which is ADC1. For the timeout, let's set 50, for example. It should be more than enough. Then let's get the value after the conversion is done and put it inside one variable. So let's create a new variable. Let's call it LDR, for example, and LDR starts with 0. Then set the LDR value, the value we get from ADC. So in order to get the value, we'll use another function. Again, hall ADC, and then control space. And there's a function called get value. Get value. We'll pass the same struct, which is ADC1. Now we have the value, we just need to print it. So let's copy this one. Command and change a bit. Let's change to LDR. Then put here LDR. This should also be the same, so we won't change. And then let's make sure our button is pressed once. This is all we need. If we're not using counter anymore, it will give us a warning. So let's comment this one. And let's try to build. Oh, zoom in a bit. Okay. Zoom. That's better. So we have two warnings. One is this one. sprintf is not initialized. Since we generated the code and then we then add the stdio.h inside the user code includes, then it got deleted. So let's add it here this time. Include the io.h. Let's build again. Now we have 0 warnings. So let's try this out. Once we press the push button, it should read the ADC and then print out the value of the ADC. Let's go back. Make sure the hex file is selected. It sometimes gets removed. Let's go to Cube IDE workspace. And then let's go to workshop day 1, debug, and then the hex file. Let's run. If we press the button now, this should have a high value. The LDR decreases the resistance value the more you increase the light intensity. So it's an inverse relationship. So if I press now, let's say it's 3796. If I increase the intensity by like 300 and then press again, it should decrease. So it's now 462. As I continue increasing, it should decrease even more, 253, and so on. 166. You can use this value then to do something inside the code, and you've successfully read the LDR value, or you have a way of sensing the LDR value. So any question regarding the first session, the ADC session?
Okay, guys, this is a Q&A session. If you have any question, you can ask in chat or you can unmute and ask. There is no question, guys. You can unmute and ask, or you can type in the chat. Okay, since I believe there is no question, so everything is clear for you guys. So we can go for 10 minutes break. We will come back at 6 p.m. So you can have some rest, and we will continue session 2 at 6 p.m. So Anas, you may.
Okay. So let's go into the.
Hello, can you hear me? Or
Yes, we can hear you. I'll continue.
yeah, sure. You can. You may start.
Okay.
Yeah.
So next is timer PWM. PWM stands for the pulse width modulation, and it's a method that of reducing the average power delivered by the electrical signal by chopping it up into discrete parts. And then the average value of the voltage and the current is fed into the load that is controlled. So basically, the pulse width modulation, the signal looks as something like this. And then the duty cycle refers to what percentage of the signal is on and what percentage is off. So if you see this one, let's say that this entire section is the period. So it's 50% on and then 50% off, compared to this one, which is 75% on and then 25% off. So this is basically the PWM. It controls the width of the pulse. Either it's 50%, 75%, 25%, or any other percentage. It is typically used in conjunction with a motor driver to control the motors. So let's jump into Proteus. In order to get the duty cycle or to see the wave, let's add an oscilloscope. So we'll go to instruments again and then add the oscilloscope. Stop the simulation first. Get the oscilloscope, and then maybe let's put it somewhere around here. Mirror it by right clicking and then X mirror, and then let's bring it closer. So now let's check the datasheet and see which pins can be used for the timer. So if we go into the datasheet, let's see. You can see that this is timer 3 channel 1, so we can use A6. So let's choose A6. If we go back, let's connect A6 to the A port, and that's it. That's all the wiring we need to do to view the waveform of the PWM we're just about to generate. So let's go into STM32 Cube IDE and press on the IOC file again. And let's go to enable the PWM for channel 1. So if you press on timer 3 and then choose channel 1, we need to choose PWM Generation for channel 1. Don't choose the no output one, since it will not have any output at the pin. We need to choose the PWM Generation channel 1. So if you go into the parameters, you notice some parameters. First, the prescaler. This is the same as the timer prescaler. So you can set the prescaler, so let's say 64. And usually when you're controlling motors, the standard is 50 Hertz for the frequency, which is around 20 milliseconds. So let's set this to 20 milliseconds. So if you do the calculation, this should be 20K or 20K. This should generate a 20 millisecond period waveform. Let's also enable the auto reload preload. And then these are the master slave mode, which we are not using currently. But if you look at the PWM Generation channel 1, we have several modes for PWM Generation, mode 1 and mode 2. You can know more if you read the reference manual, but we'll just choose mode 1 now. And then this is the pulse. So let's say I set the pulse to 10,000. So 10,000 over 20,000 will give us a 50% duty cycle, since this is half of the period, of the total period. One more thing we need to consider is the channel polarity. If the channel polarity is high, this means that channel will remain high until the pulse is triggered and it will go low. But what we need is low polarity, for the pulse to be high and then for the channel itself to be low. How many timers for this microchip? In total, there is 6 timers. There are these 3 timers. One is an advanced timer, and then 2 are general purpose timers. And then you have the system tech timer, SysTech. So these are 4. And then you have 2 timers called watchdog timers. If you open the reference manual, you have independent watchdog and window watchdog. So in total, there's 6 timers. You can also check, if you go to the datasheet's first page, 6 timers. 16-bit timers, 116-bit motor control timer, 2 watchdogs, and the system tech timer.
Sorry, I have a question. So
Yep.
for first three timers, it's 16-bit.
Yep.
Okay, yeah.
Okay. So that's it for the settings for the PWM. Just make sure that it is low so that the channel itself is low and the pulse is high. So what we need to do now is press Ctrl S to generate the code and press yes. After the code is generated, we need to also start the timer. So let's add the hold timer, but then now it's PWM. So we'll search for hold timer PWM start. We go a bit down, yeah, PWM start. You won't be using interrupt or DMA, so you just start normally. Then we'll select timer 3. And for the channel, we'll select channel 1. If you're not sure what to write for the channel, you can always press F3 on the function. And then it might show you some tips, but this is the .h. What you need to see is the .c file. So if you go to drivers and then the STM32 F1 whole driver, go to source and then the timer.c. You can see some tips for initiating the timer, but it's already auto-generated. But if you want to write it manually, the drivers have a very great explanation for the steps needed to generate different kinds of timers. So let's check for the PWM Start, which is this one. This is the outline, by the way. It shows the functions and some other different defines, like the .h file. So if you see, the channel can be either timer channel 1, 2, 3, or 4. So let's select timer channel 1, go back to main, and then paste it here. So I've started the PWM for channel 1. We don't need all of this for now. So let's comment this also and comment its values here so we don't get warnings. And then let's start to build. Control B to build. Zero errors and zero warnings. Before we go to Proteus, let me show you the timer, which is this one, timer 3 initialization. These are the settings that we just now selected: 64, 20K, enabled the preload. We're not using the slave mode, master and slave mode. The pulse is currently set to 10,000 or 10K, and the polarity is low. And this also automatically called, which is this one, post initialization. Just initializes the pin to be of speed low and to be an output. This is an alternate function since it's used for the PWM. Also enable the clock, just like yesterday. And that's it. Let's go back to main. And this is built. Let's see Proteus. If we directly simulate, we should get a oscilloscope. So we're using channel A. Let's zoom out a bit. So this is a 50 millisecond duty cycle, a 50% duty cycle. The total width is 20 milliseconds, and this is 50%. So this is 10 milliseconds and then 10 milliseconds. So if this was connected to a motor driver, the motor will be moving at half of its full speed, given that it has enough voltage. So let's try to play with the PWM that we are generating. Let's try to change the pulse when we press the buttons. So let's enter. In order to change the pulse, you can directly change the register, or you can use a definition that they have defined already, or you can deinitialize and then reinitialize with a different pulse, but that's too long. So let's use the function that they have defined. if you type 2 underscores and then hold, press Control and space, get a list of recommendations, and then you can type in timer, PWM, scroll down a bit, and you will see the set compare. You can see this is get compare, but we need set compare, which is this one. So this essentially sets the pulse value, which is the compare register. It compares the value until the counter value until it reaches this compare. So the handle is the timer 3 handle that we're using. The channel is also going to be channel 1, which is the same as this one. Then we're going to type in the pulse value that we want. Let's say this is 5,000. 5,000 should be 25% of the full period, so 25% duty cycle. Then this one. And then let's change to, let's see, 15,000. Let's say 15,000. This is 75%, and this is 25%. And initially, it will be 50%. Let's build this.
Sorry, Anas, I wanted to something. So, guys, don't forget to fill in your attendance. Link is in the chat, so fill it now. Okay, thank you. You can continue.
Okay. So now it should be at 50% duty cycle once we start. And then when we press the first button, it should be 25% duty cycle. And then for the second button is 75% duty cycle. So let's simulate. Wait for the oscilloscope to load. So this is the initial 50%. And let's try clicking on the first push button. So this should set it into the 25%. So you can see it's on for 25%, then off for the rest, and so on. If you press the second button, it should be 75%. So this is the new one, 75% on, and then 25% off. So this would give 75% of the motor speed, or the voltage to the motor. And this one is 25%. So any questions regarding the PWM generation and controlling the duty cycle? Seems like there's no question. So that was it for the second session for controlling the timer PWM. Do you want to take questions or?
Okay, guys. So this is a Q&A session. Okay, it's Q&A. Okay, so since no question, I have a question. So since you are using interrupts, so is there any library for interrupts to include?
Should already automatically be included, which is the driver, this one.
Oh,
The
you
whole
mean
timer
like
itself.
once you enable interrupt, so it will be included already?
Yeah.
Oh, yeah. Yes. Because like I remember in microprocessor section, we have to include the library for interrupt once we enable
Yeah,
interrupts.
the AVR/interrupt.h.
Yeah, that's why like I said, do we have to enable it or not?
Once we enable it inside the IOC, it's automatically included.
Oh yeah, nice. Okay, yeah. Okay, guys, if you have any question, you can ask or unmute for day one or day two. Any doubts? Anything I'm not clear? And also, don't forget to fill in your attendance, which the link is in the chat. I will share it again. And if you have any question, you can ask now.
Nice question. What are the other modes beside the PWM? If we go back to our timer and select the channels, there's input capture mode, whether it's direct, indirect, or triggered by TRC. This means that the timer captures the input at the channel pin and then compares it to something. And then the output compare is the same. It outputs a certain PWM and then compares it. And finally, the PWM generation. But this is for the general purpose timer. If you go into the advanced timer, it might have other modes like combined channels. So there is encoder mode. Encoder mode is used usually for encoders that have both channels A and B. So this would usually be the encoder mode. There's also the PWM input on channel 1 or channel 2. So this is almost the same as input capture, but it receives PWM from another microcontroller. And then there is the Hall sensor mode used for Hall sensors. This is for the advanced timer. For the general purpose timer, it just, I think, also has the same combined channels. The only difference might be the active break input. You can check out the differences inside the reference manual. You go into the advanced control timers, and then you can see this includes measuring the pulse length of input signals, which is input capture, generating output waveforms, whether it's output compare or PWM, and complementary PWM with the time insertion. This is for the advanced timers, which are timer 1 and 8, but we don't have timer 8, just timer 1 for this microcontroller. For the general purpose, it's almost the same, but we lack the complementary channel for PWM and the dead insert mode. Or these complementary PWM with dead insertion, dead time insertion. Any other question?
I have questions. So for ADC, since like, did you take a microprocessor course?
Yes.
Okay. So for ADC part, if you still remember, we have to do like ADC start conversion. So where
Yeah.
is this part in this code?
This part. Let me uncomment. So for the whole ADC start, this function enables the ADC and also starts the conversion for the regular group. So this starts the conversion. And then for the second function, this is waiting for the conversion. Wait for the regular group conversion to be complete. It just waits until either the conversion is complete or the timeout runs out. And then finally we get the value using the whole ADC get value function. That's it.
Oh, yeah. Okay, yeah. Thank you.
Okay.
Okay, like since no more question from you guys, so I believe everything is clear and everything is alright. Um, so I think this is the end for our workshop day one and day two. I won't say like special thanks to our speaker engineer and Ismail for presenting this to you for day one and day two, and special thanks to you guys for attending our workshop along day one and day two. Before we end, if you still didn't fill your attendance, please fill to get your UTM merit and also to get your e-certificate. By that, I want to say thank you and see you soon, inshallah.